Any changes in the homework? There seem to be changes in the homework and when they're due and when they're not.
It's going to be due Tuesday
Tuesday of next
instead of this Friday.
And then we'll get back on track after the break, maybe? What do we know?
That's up to Keith Sanders.
Okay.
You can send Keith Sanders email, right?
I did, but I didn't get I haven't gotten a response yet. That isn't, he just probably hasn't seen it yet.
All right. Well, I don't know. Here, let me give you candy. Okay, we better get moving. Let's see. Let's start with where we were last time. Namely, I had introduced convolutions and I showed some examples of convolutions. And the next topic is the Fourier transform of a convolution. And the remarkable thing is that the Fourier transform of a convolution is the product of the Fourier transforms. And so let me demonstrate that in some formulas. So the result that we want is F star G. Its Fourier transform at K is just F tilde of K times G tilde of K. And the way we're going to do this is, first of all, compute F star G of K, obviously. And so that will be the Fourier transform. And I'll use this standard 2π convention. E to the minus I kx, and then we'll have F star G of x. So this is the Fourier transform of the convolution. And now we're going to write the convolution explicitly. So this is dx first over root 2π. And now the convolution itself is an integral dy over root 2π. Again, minus infinity plus infinity. But now instead of phase factors, you have f of x minus y, g of y. And now we're going to rewrite f and g in terms of their Fourier transforms. And that gives us integral minus infinity plus infinity dx over root 2π e to the minus I kx. Integral dy minus infinity plus infinity over root 2π. And we're going to have this f, well, that would be f, we're going to write f of x minus y as its Fourier transform. We'd have integral minus infinity plus infinity dp over square root 2π f tilde of p e di p x minus y, the same argument as here, of course. And then g of y we're going to write in terms of its Fourier transform, which is a dq over root 2π g tilde of q e di qy. Okay. All right. Well, when you see something like this, you might worry that you've got 4 infinite integrals, one of which has an absurd integral sign because I drew it wrong. But once again, Dirac comes to our aid, and we find that these infinite integrals give us delta functions. And we use in particular equation 3.36 for Dirac's delta function. And what we see is that this is integral minus infinity plus infinity dy. So we've got 4 factors of 2π, root 2π. I'll take 2 of them and make it 2π. The other 2 will be this integral over, let us say, let me see, I've forgotten which one it is that we're going to be integrating over. We're going to be integrating over the x. The x variable then has p minus k, and so that will be delta of p minus k. Maybe I should do an extra step here. So this is integral minus infinity to plus infinity e to the ip minus k times x over 2 pi dx, and then what's left is the integral dp over, well, the 2 pi's are all gone. So this is this f tilde of p, and what's left here is minus ipy, and then this, which is the integral dq, g tilde of q e to the I qy. So this integral gives us delta of p minus k. So that's dy over 2 pi, delta p minus k, and then all the rest of this, which is dp f tilde of p e to the minus ipy dq g tilde q e to the iqy. And now when we do the, let us say, integral over q, that just is setting, I'm sorry, we're going to do the integral over, let's see, the integral over, right, the integral, yeah, we're first of all going to do another, we're going to do the integral over y now. And the integral over y with this 2 pi gives us another delta function. So what we get at this point is integral dp, integral dq, and now we have the delta of p minus k from the front. And over here, the y integral gives us delta of q minus p. And what's left is simply f tilde of p and g tilde of q. So that's all that's left. Now we do the q and the p integrations, and that just sets p equal to k and q equal to p, but p is already k, and so this is simply f tilde of k, g tilde of k, which is what the original result was, namely f tilde of k, g tilde of k. Any questions? Yes.
Is there anything significant about a convolution of a convolution?
Two convolutions.
Yes.
I don't know. I have to think about it. Why don't you hang around after class and we'll maybe try it. Okay. The next topic is Fourier transforms and Green's functions, and we've seen a hint of this in an earlier section, the examples, some of the earlier examples, but let's instead consider sort of a general case. So suppose we have P is a polynomial of derivatives. So it's like, let's see, do I give you an expression of it? No. So let us just say P of this polynomial is a sum C n ml, say, d by dx1 to the n dm dx2 to the m, dl dx3 to the l. And the point is that it's a polynomial, or in fact an infinite series, in derivatives with constant coefficients. So the important thing here is that these are just constants. And when you have a differential equation involving such a differential operator, then you can use this Green's function technique. If you're in n variables, you look for a Green's function of this polynomial differential operator. And so let's write the Green's function as a Fourier transform. Then that would be P of, well, here, let me maybe write this twice. This will be P of the various partial derivatives, and then an integral dnk. Well, let's just write the Green's function first. E to the ikx, and I'm going to call it g tilde of k, and I left out any of the 2 pi's. And now when this differential operator hits this exponential, each derivative pulls down an ik. And if it's a derivative with respect to x1, it pulls down an ik1. If it's a derivative with respect to I3, it pulls down an ik3, and so forth. And so this thing turns into an integral dnk, and then it's p of ik. So it's the same polynomial, but with the derivatives replaced by ik. E to the ikx, g tilde of k, and we want that to be the delta function, but we know that the delta function in n dimensions is dnk over 2 pi to the n e to the ikx, period. That's it. And so we have a very simple algebraic equation. The algebraic equation is p of ik, g tilde of k is just equal to 1. And so our solution for the Green's function is g tilde of k is, of course, 1 over, let's see, I've left out that it's not 1, it's 1 over 2 pi to the n. This is 2 pi to the n here. So this is 1 over 2 pi to the n p of I delta, of I, p, not p of I delta, p of ik. And so our Green's function, g of x, and I'll call it g sub p because it's the Green function appropriate to this differential operator. So there's no such thing as a general Green's function. It's that each differential operator has its own Green's function. And in fact, if you care about boundary conditions, then you'll have more than one for each differential operator. But let's avoid that detail for the moment. dn of k over 2 pi to the n. E to the ikx, and it'll be the polynomial of ik. Okay, so that's the general formula. And what we can do now is a couple of examples. Are there any questions, puzzles? Hungry graduate students who want a candy?
All of your exponentials.
Here we go. I'm sorry.
Those exponentials are dot products, right?
Yes,
K
k dot x, good question. K dot x here is k1 x1 plus k2 x2 plus dot 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 plus kn xn. Okay, an example. In 1935, Yukawa proposed a partial differential equation for the strong interactions for nuclear physics. His differential equation and the associated Green's function were like this. His differential equation was minus, we sometimes use Laplacian like that. Equivalently, this is the same thing, this triangle is the same thing as minus the divergence onto the gradient, in other words, grad squared plus m squared gy of x. And this is, of course, delta of x in 3 dimensions. So that was the differential equation. Well, that was the Green's function form of Yukawa's differential equation. But we can see then that this p is a p of grad, so py of grad is simply minus grad squared plus m squared. So once again, it's differential partial derivatives with constant coefficients. You see, if the thing didn't have constant coefficients, if there were x's in here, then you couldn't play the trick. Because, I mean, you'd have x's mixed up here, and it just would not work. So, what we get then is that g sub y of x, just using the recipe, it's now d cubed k over 2 pi cubed. So, in other words, 2 pi to the n, 2 pi to the n, e to the I kx, so this will be e to the I k dot x, and now these are 3-dimensional dot products, and we divide by py of ik. And now py of ik means that you replace grad by ik, but I squared is minus 1, so that gets rid of the minus 1. And so this is actually d cubed k over 2 pi cubed e to the I k dot x. And now this is over k vector squared plus m squared. So that's the formula. And now, let me not take up class time to do the integral. It's done as an example in equation, example 5.21. That's that complex variable theory chapter that I keep saying will be the solution to all of our problems once we get there. In any event, the answer is what's called the Yukawa potential, e to the minus mr over 4 pi r. And you see the limit of this as m goes to 0 is the Coulomb potential. And so what Yukawa proposed was that just as in electrodynamics you have a potential 1 over 4 pi r, in nuclear physics you should have a potential e to the minus mr over 4 pi r. And what he was explaining, what he was accounting for here was the short range of the strong interactions. And the range is quite short. It's 10 to the minus 15 meters or 10 to the minus 13 centimeters, a distance that is called a Fermi, named after the amazing Italian physicist Enrico Fermi. Later on, if you want, I'll tell you a story about involving Fermi and Roy Glauber. But let me get to a point in the lecture where you're all tired and you want a story. Okay, Laplace transforms. These are sort of like Fourier transforms, but also quite different. So it's integral 0 to infinity dt, e to the minus st, f of t. Okay. So you notice two huge differences. The biggest difference is that this is not a phase factor, this is a decreasing exponential. Second big difference is that we do a half, we're integrating over the half line. Well, that's of course because if we integrate it from minus infinity, this would become a huge factor, and we have almost no cases where the thing is finite. The next thing to notice is because this is only an integral over the half line, I should say, positive real numbers, and because we have this decaying exponential, that means that we can define the Laplace transforms for functions f of t that don't have Fourier transforms. So there are functions that, as long as f of t doesn't grow faster than an exponential, it'll have a Laplace transform. So that's the idea, and I'll just give some examples. Suppose f of t equals 1. Well, then you can just do this integral, and you find f of s is just, maybe I should say what the integral is, it's just dt to infinity e to the minus st, and that's just equal to 1 over s. You can even have f of t be an exponential, e to the kt, and now what you have is an f of s, which is then integral dt of e to the minus s minus t, s minus k, sorry. And this is 1 over s minus k. So this works as long as the real part of s is greater than k. So this is a damped exponential. Let me just mention, and of course once you've done this integral, you can say, well, in some sense, in other words, this Laplace transform, which is only defined for real s greater than k, gives us something that is defined for all s. So it's one of these cases where you do something legitimate and you get a more general result than you hope for. Analogous examples are the Laplace transform of the cosh e to the minus st. I'll just write it this way. Cosh of kt, this is cosh, but one can abbreviate it like this. This is then s over s squared minus k squared. If instead we do the sinh of kt, we get k over s squared minus k squared. If we have instead cos omega t, cosine, we get s over s squared plus omega squared, and if we have sine omega t, we get omega over s squared plus omega squared. So you notice these are all essentially the same. The reason they're essentially the same is that each of these functions is a pair of exponentials. They're real exponentials in these cases and imaginary exponentials in these cases. Okay, I'm going to skip example 3.12. Those of you who are interested can, of course, read it. Yes?
In the book you talk about, like in this first example where you just have f of t is equal to 1, you say it's well defined for real s greater than 0 and square integrable for real s greater than epsilon, but how is that any real s greater than epsilon?
Oh, it's square integrable on the real line from epsilon out to infinity. That's what I meant.
Oh, okay.
You're right. That I could have said that better. And
wait, so do you mean that s? Because what you just said is for t varying between 0 and infinity, or between epsilon and infinity. I'm just confused.
It's square integral on the interval epsilon infinity. It's square integral on a certain interval. Epsilon comma infinity, like that. That interval.
Oh, okay. You mean the Laplace transform is square integrable? Yes, okay, I understand now. And otherwise it would be divergent at 0 because the Laplace transform is 1 over s.
Yeah.
I understand.
Okay. All right, good. So we're going to skip that example, which, however, is interesting. And now think about derivatives and integrals of Laplace transforms. So let me get a piece of chalk here. And, well, it's pretty obvious. I mean, you just differentiate this with respect to s, and you bring down a minus t. So the equation then is dn of f of s ds to the n is integral 0 to infinity dt minus t to the n e to the minus st f of t. So in other words, when you differentiate, it's effectively replacing the function capital F of t by f of t times minus t to the n. Yeah, that's a little better. So as an example, we can look at, I guess, the function, this case that you were talking about, and we can say minus 1 to the n dn of s inverse ds to the n. This is n factorial over s to the n plus 1, and that is the integral 0 to infinity dt e to the minus st. And this is t to the n. So we learned that the Fourier transform of t to the n, Laplace transform of t to the n, is n factorial over s to the n plus 1. Now, that's differentiating f of s, but we can also differentiate f of t. And or in other words, we can consider the Laplace transform of the derivative of f of t, namely f prime of t. And what we do is we just integrate by parts, 0 to infinity dt, and if we do that from first principles, then we rewrite this as d by dt e to the minus st f of t. So this, when the d by dt hits f, we get the thing we want. When it hits this, we need something, we get something we need to cancel. So we cancel by writing minus f of t d by dt of e to the minus st. Okay. This one, of course, we just do the integral, and so that gives us e to the minus st f of t evaluated at 0 and infinity, and we'll assume then that f of t, as t goes to infinity, doesn't increase as fast as this, so we get 0 there. And so, and then the other term, of course, d by dt of e to the minus st is just minus, it's just multiplied by minus s. The minus sign cancels, and so what we have is 0 to infinity dt f of t s e to the minus st. And so all of this gives us minus f of 0 plus s. You pull out the s, and what's left is f of s, so s f of s. Okay, so when you take the Laplace transform of a derivative, what you get is s times the Laplace transform of the function, and then minus the function evaluated at 0. So it's a curious thing, but straightforward. And You can also do something else. Namely, you can take this thing here and you can do the indefinite integral with respect to s. And I've been writing that as, I don't know if there's a standard formula for that that's universally sanctioned, but I'm writing it this way. That's the indefinite integral, so that's integral ds1 f of s1, and this then is integral 0 to infinity dt, and so we integrate e to the minus st indefinitely, we get e to the minus st over minus t times f of t. And so that means that the indefinite integral of the Laplace transform is the Laplace transform of the function f divided by minus t. Is that a question or are you stretching? And in general, the nth indefinite integral f of s is integral 0 to infinity dt e to the minus st, and it's then the Laplace transform of minus t to the n. Now, these integrals are usually well defined, except maybe at s equals 0, and the idea is that the problem that occurs here is that as t goes to 0, we've got a 1 over t to the n, and so for these indefinite integrals to be well defined, f has to be suitably small at small t. Otherwise, the integral is bad at t equals 0. So that's just one of the things you have to keep in mind, even though we're in physics departments and we're in physics department and we don't, we can approximate things. You've got to make sure that you don't do something that's completely crazy.
So when you do your indefinite integral e to the minus st, normally we would get a constant plus add a constant added to that. Are you just leaving that out?
That's right, yeah.
Okay, just
To keep the formula simple. Okay, now let's talk about Laplace transforms and differential equations. So you can, we did Fourier transforms and differential equations several times, and now I'm going to be thinking about a polynomial in, let's just stay with one variable. So suppose we have this differential equation, where again this is a polynomial in d by ds with constant coefficients. And what we do is that we then write f and j as Fourier transforms. So we say, of course, f of s is integral e to the minus st, big F of t, dt, and j of s is integral 0 to infinity dt e to the minus st, j of t. And now it's very similar to what I did over there. Namely, our equation is 0 to infinity dt e to the minus st. Well, when d of d by ds hits f, it just brings down a minus t. So we get p of minus t. And this is equal to e to the minus stj of t dt. And so the solution is that f of t should be j of t over f of p minus. Okay. And Now, this gives a solution to this inhomogeneous equation. P of d by ds on f of s equals j of s. That's inhomogeneous because the right-hand side is not 0. And one way of dealing with that is, once again, to rely upon Dirac. So we want a solution of P of d by ds f of s equal to 0. Well, we can say f of s is integral e to the minus st delta of p of minus t h of t dt. Because now when p of d by ds hits this thing, what we get is an integral e to the minus st p of minus t delta of p of minus t h of t dt. But that means that the only t's that survive are the t's such that p of minus t is 0. But if p of minus t is 0, then it comes out as a factor and it's 0. And so this is 0. Okay. So we can then have a solution, namely 0 to infinity e to the minus st j of t over p of minus t dt plus integral 0 to infinity e to the minus st delta of p of minus t h of t dt. And notice h is basically arbitrary, so you get a broad range of solutions. Now, what is true is that the general solution of an inhomogeneous equation is a particular solution of the inhomogeneous equation plus the general solution of the homogeneous equation. Whether this is totally general, I don't know. But it's at least a good start for being reasonably general. Yes?
And that solution is unique, so we can go to and from Laplace space.
Unique? Did you say unique? Well, we're looking for the general solution, so we want something that's not unique.
Yes, so the question was more, can we switch between Laplace split space and normal space with impunity and know that we're not destroying information? Or is it like taking the square root and squaring things where you do it and then you might lose the solution?
So let me see if let me try to understand what you're saying. Are you saying that, here, maybe move the camera a little bit. Are you saying that if we start with f of s, are you asking if this is unique?
I was actually looking f of s and then go to f of epsilon and then back to f of s.
F of epsilon?
It looks like
T.
an epsilon is
Sorry.
supposed to be a t.
Fine, Dave.
Oh, you're right. This is
can
a
we
t.
switch?
Goodness, this is t. Sometimes I don't write clearly.
If we switch from s to t and back to s, is that going to be the same s and nothing has
You know,
gone
you're
wrong?
just now getting to the topic that I'm about to do. In other
Okay.
words, given f of s, how do you find f of t? So this is inverting the thing. And that's the next topic. So let me do that topic. And then maybe after that topic we can know the story. Okay. So how do we invert the Laplace transform? So we're given f of s. We want to find f of t. And so the first thing that we do is we promote f of s to a complex variable. And so we say this is f of s plus iu is integral 0 to infinity dt e minus s plus iu t f of t. Okay, so that's just, so to speak, generalizing the Laplace transforms from real variables as to complex variables. The next thing is we say, well, we're going to massage this right-hand side, so let's pick a value of s that's big enough so that we can do whatever we want over here. In other words, we want this integral, we're going to do the following. We're going to integrate over here. And of course, what we're really doing is, once again, leaning on Dirac. It's just amazing how something like 80% of what physicists need was done by Dirac. So we form this integral. We're going to integrate over u. We're going to use a Dirac delta function in a minute. So we multiply by e to the s plus iu and t on this f of s plus iu. And what is that? Well, that's going to be an integral minus infinity to plus infinity du over 2 pi, 0 to infinity t prime, yes. All right, so I'm going to change this to a prime. And then what we have is e to the s plus iu times t minus s plus iu t prime. And what's left here is f of t prime. So I want to pick a value of s that's sufficiently big so that this integration, all this integration makes sense. And we're integrating over t prime, and so we have an e to the minus s t prime, so that's going to suppress things. All right, anyway, we now use the delta function formula because this du over 2 pi e to the iut minus iut prime is delta of t minus t prime. So what's left here is dt prime delta t minus t prime. And the only other thing left is f of t prime. And so that is just f of t. Okay. So this is the desired formula. In other words, f of t, the inverse Fourier transform is e to the st integral minus infinity to plus infinity du over 2 pi e to the iut f of s plus iu. And what can we say about that? Well, we're starting with f of s. The first thing is, can we promote f of s to a complex variable? And presumably we can. And then, will it have, this is effectively a Fourier transform, because it depends upon what f of s plus iu does. Might do something weird, okay? So whether that integral converges or not is not obvious immediately. It depends on what f is. But this is the inverse formula, and this is sometimes called a Bromwich integral. Sometimes people call it a Fourier-Mellon integral. Anyway, it's the way you get back. Any questions? Okay, really quickly, the story that Glauber told me is actually a somewhat a sad story. It was that Fermi and Glauber were in the Swiss mountains, and presumably at some summer school or something like that. Anyway, and they were going to take that opportunity to buy some hiking boots. And Glauber thought he had a really good pair of hiking boots. And Fermi bought a cheap pair. And so Roy asked Fermi, why did you buy a cheap pair? And Fermi said, well, I'm not going to live long enough to wear them on. I didn't want to waste money. The problem was that Fermi smoked cigarettes, first of all. And secondly, he did both experimental and theoretical physics, and he was in the Manhattan Project, and he built the first pile of pure carbon bricks and some uranium, and concentrated to 3%. Also, he did scattering experiments, and somebody told me the story that he would sit there doing his theoretical physics while in a room with the cyclotron. The beam would come out, go across the table that he was writing at, and he would have the counters on the table and a timer, and the timer would go off, move the detector and change the azimuthal angle or the scattering angle by so many degrees, click the timer again, and you go back to his theoretical physics. Well, you know, there's a certain amount of scattering and radiation. And so I don't know. I suspect it was mostly the cigarettes. Cigarettes, by the way, kill partly at least by radiation. What happens is the stuff that sticks there in the lungs is polonium-210, which the Russians used to kill somebody in England maybe 10 years ago, and also lead-210. And both isotopes are radioactive, and both of them are heavy metals that are poisonous. So when you smoke, you wind up poisoning yourself and giving yourself a dose of radiation in the worst place, the lung. So the lesson is, don't smoke. Anyway, that's a sad story. Okay, let's go back to partial differential equations. And let's again consider a partial differential equation d1, d2, dn on f of x1, x2, xn equals g of x1, x2, xn. So this is an inhomogeneous partial differential equation. And here I'm using a notation dj is partial xj. If g is 0, then the equation is homogeneous. If not, it's inhomogeneous. So anyway, we're going to write f of x, and let me use just the notation x for the whole family of x's, and k for the whole family of k's, even though in the book it's written more generally. So f tilde of k, e to the I, kx, and I'll put a dot there, dnk. So this is an n-dimensional Fourier transform. We're going to do the same thing for g. Gn of k. And now I'm being very general here. So once you think about this part of this particular section as being very much in the spirit of the physics department, and if I tried to give this lecture over the math department, they'd be shouting and they'd throw tomatoes at me and so forth. Nonetheless, I think you'll see that it actually works. And, whether the mathematicians will catch on in 100 years, maybe. Okay, so let's now apply this differential equation, and of course, what we have here is dj to dm on f of x will be the same integral f tilde of k, but, oh God, it's almost Chinese, isn't it? F tilde of k I kj to the m e to the I k dot x dnk. Oh, and when I started to say that this is going to be very much in the spirit of a physics lecture, is we can think about these integrals on k as being ordinary integrals from minus infinity to plus infinity, in which case it's a Fourier transform, or we could think of them more generally, that maybe the k's are running along the imaginary axis or some other contour. So this is a much more, so I'm thinking very generally here. And so when we apply this differential operator with constant coefficients to f, what we get is p of p of the derivatives on f of x is integral f tilde of k, p of I k, e to the I k dot x dnk, and we want that to be integral g tilde of k, e to the I k dot x dnk. Okay. And so obviously the algebraic equation is f tilde of k, p of I k has to be g tilde of k. And so in other words, the solution is what we're looking for. F tilde of k then should be g tilde of k divided by p of I k. And so that means that the inhomogeneous solution, f of x, is integral e to the I k dot x. Remember, there are n k's and n x's, so we're summing there. G tilde of k over p of I k dnk. So that's the inhomogeneous equation. The homogeneous equation, I'm going to use the same trick as I used over there. I'm going to say f homogeneous of x is an integral e to the I k dot x delta of p of I k h of k, where h is essentially arbitrary, dnk. And the reason this works is that when you hit this function with p of grad, so p of grad on the homogeneous function is an integral e to the I k dot x delta p of I k h of k dnk. And the delta function is non-zero only where this is zero, so the whole thing is zero. So our solution then is, and maybe I'll go to, is this. So it's this n-dimensional Fourier transform of g tilde of k1 kn over p of ik1 ikn plus delta of p of ik1 ikn h of k1 kn. And we need a bracket there, and then dn. Okay. So that's more or less the general solution. And I think this is this has some use, and I'll give a couple of examples of it, but I'm a little worried about the time. what do you think? Let's see, how much of the homework is due Tuesday? How much of chapter 4 do you need? Well, how many problems are there from chapter 4?
Just one?
Just one.
That's it? Really? Oh, okay, well, these, I mean, when you can do, there's a, MATLAB does infinite series. And that's, I guess, equivalent to the Intel test that I mentioned. And in fact, let me give you the command.
MATLAB to do these tests. Is that what we're getting out of this? 4.1 is testing the convergence of infinite series.
I don't know if this is absolutely the best command, but... Okay, in MATLAB, all right, you do SimSum, SYM, SUM. For instance, now let me just give you an example. X hat k, that means x to the k, divided by factorial k, so that gives you that. You then say you're summing over k, 0 is the first, and INF is the last, meaning infinity. And this, it may give you exp to the x, or it may, if you say what x is, it would then evaluate it. In any way, SimSum is a way of doing these. There may be a better way in MATLAB. So in that case, I think I can spend a little more time and do a couple of examples here.
I just realized that's the exponential function.
What?
I just realized that's the exponential function. I'm okay.
Yeah. Okay, so let's think about a free scalar field. We have grad squared minus d by dt squared minus m squared phi of x equal to 0. This actually is the equation Yukawa wrote down. So I'll write down Yukawa. And so let's use this approach for that. In this case, we have a homogeneous equation. So we'll use, so we don't have any g, we just can throw in an arbitrary function h. So what we'll say then is that phi of x is going to be an integral e to the I k dot x phi tilde of k d fourth k over, I did 2 pi squared because I've got square root of 2 pi to the fourth. And I could have done this, maybe should have done this with this being k1x1 through k4x4. But what I actually did was to use the standard physics notation for these 4-dimensional products. K dot x for the 3-vector part minus k0t. So this is a Lorentz product. It's just a minus sign on one of these variables. That's not a big deal. So now, if we act on it with grad squared minus d by dt squared minus m squared on phi of x, and since this thing is squared, it really essentially makes no difference. You get an integral minus k vector squared plus k0 squared minus m squared e to the I kx phi tilde of k d fourth k over, well, pi squared. That's not going to make any difference either because it's a homogeneous differential equation. Equals 0. And so now we need this algebraic equation, which now is minus k squared plus k0 squared plus m squared by tilde of k should be 0. And then the solution then is going to be, and by the way, this something very similar to this occurs in the case of photons, where you just set m equals 0. And of course, for photons you have, instead of one field phi, you would have 4 different fields phi. And so then you would say that phi of x is an integral delta of minus k vector squared plus k0 squared minus m squared e to the I k dot x h of k d fourth k over 2 pi squared. Now h is arbitrary. That's how we get the most general homogeneous solution of the homogeneous equation, which of course the equation we have. First of all, we have to deal with this delta function. The delta function is a function of g of k, and we can think of it as g of k of k0. And this is k0 squared minus k vector squared minus m squared. And we just rewrite that as k0 minus square root of k squared plus m squared. This is the 3-vector plot. Times k0 plus square root of k vector squared plus m squared. And this has zeros at k0 equal to plus or minus, obviously, square root of k squared plus m squared, which I'm going to define as plus or minus omegas of k. This k being a 3-vector k. Okay. And of course, g prime, the derivative the derivative of g of k is going to be the delta function at these two roots plus, in fact, maybe I should write that explicitly. I somehow skipped that in the, all right, so let me just say let me just rewrite this then in terms of, so in other words, delta of g sub k of k0 is going to be, first of all, delta of k0 minus omega k divided by g prime at omega k in absolute value. And of course, what is g prime? Well, it's g prime k at plus or minus omega k. This means that we're differentiating with respect to k0. And if we take its absolute value, it's just 2 omega k. Omega k being the positive square root. And so this is, and in fact, this thing is since it's absolute value, it's the same. So this is absolute value of 2 omega k, and this one is also absolute value of 2 omega k. So that's how we interpret the delta function. So that's an example of delta functions of more complicated arguments. Now, if we substitute this in there, what do we get? We get phi of x is an integral, and you see we have a d fourth k here, and d fourth k is dk0 d cubed k. And so this is then, when we do that integration, we get a we get H evaluated at omega k, H evaluated at minus, H evaluated at k0 equal omega k, H evaluated at k0 equals minus omega k. And so what we get here is e to the I k dot x minus omega kt, what I'll call h plus of k, now it's k vector, plus e to the I k dot x plus omega k t times h minus of k. And all that is d cubed k, and we've got 2 pi squared and 2 omega k. Omega k being intrinsically positive. I didn't need these out, just value signs, so we'll make it rid of them. Okay, now, and these h plus or minus of k is h of plus or minus omega k, k vector, this being a 4 vector. And so that actually, well, no, that's okay. That's okay. All right, now, omega k is an even function of k. It involves just k vector squared, k vector dot k vector. And so in this integration, we can flip k to minus k, and it doesn't make any difference. And so what we get is phi of x equals integral e to the I k dot x minus omega k t h plus of k plus e to the minus I k dot x minus omega k t h minus now of minus k vector, and still d cubed k pi squared 2 omega k. Now, let's recall that this basically is writing a real function phi of x as a Fourier transform. And in that case, what we know is that since it's real, h minus of minus k is equal to h plus of k complex conjugate. And that's if we're thinking of this as a classical field. If we're thinking of this as an operator, then what we have is h minus of minus k is h adjoint of k. In any case, what we get is the standard formula for a scalar field. Phi of x integral e to the I k dot x minus omega kt. Now I'm just going to introduce a notation. A of k is going to be h plus of k. Remember that was arbitrary. Over the square root of 4 pi omega k. And so this thing is a of k plus e to the minus I k dot x minus omega kt a dagger of k, all that, and now we have d cubed k square root of 2 pi cubed 2 omega. So this is the standard formula for a scalar field. And it's, okay, anyway. I think I'll skip the rest of this example. I urge you to read it, though. It's just a few more lines, 10 lines or something. But let's now use our recipe for going from a Fourier transform to a Fourier series to write the field as a Fourier series as opposed to a Fourier transform. And we do that, what we say is that phi of x then is, since we're only in 3 dimensions, in other words, this is basically a function of, I'm thinking of it as it's a 3-dimensional Fourier transform, so we're in 3 dimensions. We divide by L cubed, which is the volume. We then have a sum over k, 1 over square root 2 pi cubed, 2 omega k, and then we have a of k, e to the I, kx minus omega kt plus a dagger k, e to the minus I, kx minus omega kt. Anyway, what's usually done at this point is we change from a of a continuous variable. Well, of course, this is really defined. Once we've gone to the Fourier series, what we're saying here is that these k vectors here are no longer continuous, but rather k is 2 pi over L times some integer n. Triple of integrals. In the text, it's LNM. And when we finish, let's see. Oh, it's not simply that, it's a square root of 2 pi cubed over v. And then this thing becomes a sum 1 over square root of 2 omega k volume, and then ace of k, phase factor e to the I, let me just do this kx, plus ak dagger e to the minus I kx. And now, so let me put back in some of the quantum that we skipped. The commutation relations for A conventionally are A of k, a dagger of k prime is Dirac's delta function, k minus k prime, and in this case, with this normalization, we have the commutator of a of k with a dagger of k prime is now Kronecker delta of k and k prime. So you see the normalization is actually right. So this recipe that we got for going from Fourier transform to Fourier series is useful and correct and so forth. All right, so I'll stop now. What is the date? 1 October?